Hello guys, welcome back to TechDose, and in this video we will see using a robot to print the lexicographically smallest string problem, which is from Leetcode number 2434. Let's now look at the problem statement. In this problem you are given a string s and a robot that currently holds an empty string t. Apply one of the following operations until s and t are both empty. Remove the first character of the string s and give it to the robot. The robot will append this character to the string t, and remove the last character of the string t and give it to the robot. The robot will write this character on paper. We need to return the lexicographically smallest string that can be written on the paper. So if you look at the first example here, then we have z, z and a. Right. Now, according to the first constraint, we will be parsing from left to right. We will be seeing the first character. Okay. So this is the string s. There will be another string t, and you can append this z to the end of t, right? And you now have two choices, whether you can take this out and print it in the resulting string, or you can keep it there. So if I keep it here, it will be optimal. You will see it later that when I see the third character, then what I do is I will be taking this out and printing it, and then take out the rest of the characters as well and print it. So this will be giving me the lexicographically smallest string possible by following these two possible rules, and this is how I get a double z, right? If you look at the second example, you have the string s as b a c, and in this case if you try to take another string t, where if you see a b, you will append it, but you will not take it out because there is a smaller character on the right hand side. So if you pick the smaller character and keep it on the leftmost side, it will give you the lexicographically smaller string. So you will not take this out. When you push a, then there is no smaller string on the right hand side, so it is better that you take it out and print it. And you will see that even pushing c and taking it out is not optimal. You take out b because there is no smaller character on the right hand side than b. So take out b and then take out this c. When you see c, then you can just push it and take it out. This is how you get ABC, right? So when you move from left to right, then seeing a character, let's say character c, you will always be taking it out and including it into the result if there is no smaller character on the right hand side. This is how you will be printing the lexicographically smaller string. Now if you look at the constraint, the number of characters are 10 to the power of 5. So you cannot write an n square algorithm, as it will be 10 to the power 10, way beyond your 10 to the power 8 limit, which is for 1 second standard. So you can at best do n log n or maybe order of n. So I hope the problem statement is clear. In this case, only English letters are allowed, which are lowercase. So in this problem, we need to generate the lexicographically smallest string. So in the given string here, I have taken 4 characters c a d b, and you can understand this in the form of the graph. Okay, the lexicographically smallest string would be abcd, but this may not always be possible. How I generated abcd? By just sorting it. If you sort the given string in ascending order, that means non-decreasing order, then you will get abcd. But we may or may not be able to generate this particular string because we cannot simply sort it. There were rules which were mentioned about how we can construct a string, right? So in this case, the arrangement rule number 1 was to parse from left to right. Okay, we need to parse this entire string from left to right. The second rule is to put the parsed character in a string t, which will behave like a stack. So whenever you see a character, then you can choose to put it in the string t. Actually, you must put it in the string t. And then the third rule says that you can remove any number of characters from the end of the string t. So removing any number of characters at the end and pushing the characters at the end makes it behave this string like a stack. So that's why I have written a stack. So we can remove any number of characters at any point of time from the end of the string t, so as to produce the lexicographically smallest string possible. Now let's say that you have seen this first character c, and you have pushed it into the string t, and you have taken a result where the result will be containing the lexicographically smallest string. Then will you take this out and then you place it in the first position, Well, the first position will be the highest weighted position, right? Because when you move in a string from left to right, the leftmost position is the highest weighted and the last position is the least weighted. Okay, in the lexicographical comparison. So you will place this C in the beginning only when you are absolutely sure that there is no one smaller than C on the right hand side. But if you look at the right hand side, then yes, there is a character which is smaller than C on the right hand side. So definitely C cannot be the first character, and so C will remain in the string T. C will remain in string T. Now when you go to A, then you see, will you push this A? Definitely you have to push it, but will you take it out and print? That means keep it in the initial position of the result. Well, that will depend on whether you have any other character on the right hand side which is smaller than A. So there is no character on the right hand side smaller than A. So you take it out and you print it simply. And now you have to continuously keep on checking for all the characters one by one. But in this case again, when you check for C, are there any characters which is smaller than C on the right hand side? Well, A was a candidate, but A has already been printed, so this will not be considered for this C. But there is another B on the right hand side, right? So at this point of time, C cannot be taken out. Now you check the next character, which is D. So D will be pushed into the string T. Okay, now can I take it out and print it? Well, there is a character on the right hand side which is smaller than D, so D cannot be coming to index 1. Okay, now you go to the next character B. Okay, now when you look at B, then should I take it out and print it? Well, that will depend on whether you have any smaller character on the right hand side. So there is no character on the right hand side, so definitely you have to take it out and print. And similarly for this D, there is no character on the right hand side smaller than D because this B has been already used, so D will also get printed. And so the last character which is left is C, and there is no character on the right hand side smaller than C because both A and B have been used. So C will also be taken out and C will be printed. So the lexicographically smallest string that we can form from CADB was ABDC and not ABCD, right? Because we had to follow certain rules. So I think this is entirely clear that at any point of time, for any character, if you are pushing that character at the end of string T, then whether or not it will be taken out and included at the end of result at that very moment will depend on whether you have any character on the right hand side smaller than the current character that you are looking at. So if you solve it in the simple approach, then don't you think that for any character you have to iterate for all the characters on the right hand side and see if there is any smaller character? That has to be repeated for all the characters, right? So the time complexity in this case will become order of n square, and you know that n square technique is not going to work in our case, right? So what to do? In this case, if I can just remember the items which are already present on the right hand side with precision, then I can say that if I can get the smallest character on the right hand side of any given character, then I can make this entire algorithm run in just order of n time, because for any character, finding out if there is anybody smaller than this particular character would require you to traverse the entire string. Okay, so that was taking additional O(n) time, but if you can get this in O(1) time somehow, then this entire algorithm will become O(n). So in order to maintain that, what I can do is I can do pre-processing in such a way that I can create a KV pair where the key is the character and the value is the frequency, and this entire map will be containing the right frequency of all the characters. That means initially I can just parse this entire string and keep the frequency of all the characters. C is occurring one time, A is occurring one time, D is occurring one time, and B is occurring one time. If I can do that, then at any point of time, like let's say at C, I can simply iterate on this map keys and I can check if there is any character smaller than C which has a frequency greater than 0. And how many entries are possible, by the way? In this case, only 26 entries at maximum, because all the letters are smaller case, right? So for every item, just to check how many items is there any item on the right hand side which is smaller than the given character, can be observed in just O1 time, having done the pre-processing in O(n) time, right? Then after this, once you check that, okay, there is another character which is smaller than C, A on the right hand side, its frequency is 1. Then when you go to the right hand side and skip this C, then this C will be appended at the end of the string T, and its frequency will be reduced by 1 and it becomes 0. Okay, and simply that will be the method. Again, for this A, you will be checking if there is anything on the right hand side smaller than A. So you check that whenever you reach somewhere, you can reduce the frequency and there is nobody smaller than A on the right hand side which has frequency greater than 0, so you can immediately print it, right? So that is the process that we will be following. So let me show you with a dry run how to do that. So in this case, the string given is CADB, the same, and this is the graphical representation, and I will be maintaining a map. Okay, so this is the right frequency map. So it will be of size 26 for A to Z, and I have already pre-filled all the values. A, B, C, D are all occurring 1, 1, 1 time, right? And the rest of them are all occurring 0 number of times. Now I will be iterating for the first character, that means C, and check out. Whenever you see a character, you will be pushing it into the string T, and then whether it will be included in the result will depend on if you have any element on the right hand side which is smaller than C, right? So first of all, when you appended this, you have to decrease its frequency by 1 because this has been seen. Now if you want to find out if there is any character which is smaller than C on the right hand side, you look at the right frequency map, you iterate through it, and the first item that you find having the frequency greater than 0 will be the smallest character, isn't it? In this case it is A, because this is all in increasing ASCII value, right? When you go from A to Z, it is in increasing ASCII value. So the first character where you find the frequency greater than 0 is the smallest character on the right hand side. It is A. The current character is C. That means we have a smaller character on the right hand side, so this cannot be popped out. Okay, so let it be in string T. When you see A, you push it, you decrease its frequency, and then you check on the right hand side what is the smallest character. It is B. So current character is A, which is smaller, so take it out and include it in the result. Now you continue to do that with all the characters in T until you find that, let's say for this character C, the smallest character being B on the right hand side which has frequency greater than 0, hence C cannot be taken out. Okay, now we do the same thing for D. We will append D at the end of the string T and then check. You will reduce the frequency of D definitely, then check the smallest character on the right hand side. It is still B. Okay, that means D cannot be taken out. Now you check for this B. So B will be appended, B's frequency will be reduced. Check out the smallest character on the right hand side. If you find everyone's frequency is 0. So if everyone's frequency is 0, this means that you can simply take this out and print it. Okay, now for this D, again all the frequencies are 0, so you can take it out and print it, and similarly for C you can take it out and print it. So you will get ABDC, right? So this is how you can maintain for any character what is the smallest character on the right hand side by doing a lookup on this entire map in order of 26 time, which is equivalent to order of 1 time, right? Because this array size is 26, and you can build the lexicographically smallest string. So I think the future reference technique is clear. So let's do a dry run, and in this case I have taken a string size of 8 and I have already calculated the right frequency map. Here I have shown you with the graphical diagrammatic representation as well, and now we will try to process with the same idea. So when you go to any character, you append it in the string T and then reduce its frequency. Now iterate through this entire map and find out the first character where frequency is greater than 0. So this is A, current character being C, which is larger, so it cannot be appended to the end of a result right now. Go to D, okay, append D, reduce its frequency. Again go through it, the smallest character being A, smaller than D, so it cannot be taken out. Go to A, append A, reduce the frequency of A. And now again go through this entire right frequency, smallest character being a, which is not smaller than this a, right? So this a will be taken out and it will be appended. Now check for d. Again, the smallest character being a, d cannot be taken out, right? So we will leave it at this position. We will go to the next location, which is c, append c, reduce the frequency of c by 1, check the smallest character, again it is a, and so c cannot be taken out. You go to b, append b, reduce the frequency of b, again pass through and check the smallest character, it is a, so b cannot be taken out. Go to d, append d, reduce the frequency of d, again find the smallest character a, so d cannot be taken out. Go to a, append a, reduce the frequency of a, find the smallest character, it will be c, smallest character where frequency is greater than 0, right? So a is smaller, therefore a will be taken out and it will get printed. Check for d. Again c is smaller than d, so d cannot be taken out. Go to c, reduce the frequency to 0, append the c to the end of the string t. Now check out. Can you take out this c? Find the smallest character. There is no smallest character because everything is 0, right? So you can return a z value saying that z is the smallest character, right? This is a default return when you could not find any character with frequency greater than 0. So in such case, c will be taken out, c will get printed, and you can imagine that all of these will be taken out. D, B, C, and DC will also get taken out because all the frequencies are now 0, so everyone will be smaller, right? And the final answer is AAC, DB, CDC. So I think this entire process of generating the smallest lexicographical string according to the mentioned rules are clear. So in this particular case, we are pre-processing this entire write frequency map in order of n time to build the map, and then this map entries will be 26. I will be taking an array for it, so it will be of size 26 from A to Z. Now for every character, it is pushed exactly one time into string t and popped only one time. So you may be visiting a character maximum 2 times. In each visit to the character, you might have to find the smallest in the write frequency map. So in that case, since you have total n number of characters, you are visiting it 2 times, and every time you visit, you are parsing through the entire write frequency in order of 26 time. So if you take this time complexity, you can imagine it to be order of n, right? So that is why the time complexity is going to be order of n. And in this case, you know that the map is of only size 26. So you can assume that the space complexity is going to be order of 1, where we are not considering the storage for the resultant string, the time complexity being order of n. I hope this is clear. Let's now look at the code. If you are someone who is looking to prepare for top product based company within a limited time of just 3 months, then we have brought for you both the DSA and the system design live interview training program. The most important feature of this program is you get a filtered and condensed structured curriculum, in-depth discussion of all the topics, and my guarantee of your understanding, one-on-one guidance with me, and live weekend classes. To know more about the training, you can WhatsApp us on this given number. In this problem, we are given the string s, and I am finding the size of the string. Now this is the pre-processing step where I will be calculating the frequency of each characters and storing it in the write frequency map. Then I will take the string t and result. Okay, then I will be iterating through all the characters one by one in the given input string. Find the character, current character will be pushed into string t and its frequency will be decremented. After that, we will be trying to take out as many characters as we can from the end of the string t if the end of the string t is the smallest character when you compare with the smallest character present in the write frequency map. Okay, so keep taking it out and keep pushing to the end of the resultant string. Okay, if you cannot do any further taking out of the items, or if the string t becomes empty, you come out of the loop. And then you go to the next character, and this will be repeated until the string ends, and finally you will return the resultant string. So I hope this entire technique is clear. In this case, you see this smallest character finding is just iterating over all the 26 entries, and the first entry where you find a character frequency greater than 0 will be the character that I am looking for, right? Otherwise, if you could not find anybody, then you will return z, okay, which will serve our purpose. So I think everything is clear. If you still have any doubt, then feel free to comment below and I'll try to help you as soon as possible. See you guys in the next video. Thank you.